Hello everyone. So this is the first lecture of EEE 4483 Digital Electronics and Pulse Technique. So in this lecture we will just review some of the things we have already learned in the previous semesters. So as you know, previously I discussed that for this course we have some prerequisites. We have to have understanding of electronic devices and circuits and also digital logic design. So in this lecture we will just get some idea about whatever we have learned in the previous semester about electronic devices and circuits, so that we are in the same page. So let us start. For this lecture I followed these three books, but I don't think you have to thoroughly go through all of these books. For this particular lecture, if you just go through the contents I have prepared here for this lecture, that will be enough. So let us start. So I think most of the things I will discuss here, you already know them, maybe from your intermediate level or maybe from previous semesters. But still, I will go through this so that we can review some of the basics we need to understand for this course. So semiconductors. Semiconductors are a special type of materials which have property in between conductors and insulator. So when we talk about insulators, insulator doesn't have any property that permits flow of carriers or electrons inside of it, right? And for conductor we have that facility that electrons actually generally easily flow in the material. But semiconductor have a property that is in between these two types of materials, and what we see generally is in room temperature or whenever you have given enough thermal energy to the semiconductor, so some valence electrons can gain enough energy. So valence electrons means at the outer layer you see the electrons that actually helps us to form bonds. These electrons can gain enough energy to jump across the band gap and into the next band, which is conduction band. And whenever we have electrons in conduction bands, these electrons can freely move through the semiconductor lattice, and that will actually generate or actually permit us for carrier flow or electron flow. So from this discussion we have some terms we generally use to denote semiconductors, like intrinsic semiconductor, so highly pure without any kind of impurities added to the semiconductor. These kind of semiconductors are called intrinsic semiconductor. And also intrinsic carrier means the electron holes generated only by thermal energy. So in the intrinsic semiconductor, just by one means we can generate carriers, electron hole pairs, which is by increasing the temperature to that material. So this is called intrinsic carriers. Now we talked about intrinsic materials. Now we will see how we can make that intrinsic material impure for one benefit. So what is that? So we are talking about N-type and P-type materials. So it's written here, formed by doping pure semiconductor with group 5 elements, okay, that have 5 valence electrons. So if you look at this particular figure here, you see silicons are the semiconductors actually, and here you can see SB or antimony. This is a pentavalent element, group 5 elements, which have 5 electrons at the outer layer, and it is creating this bond with other silicons. But at the end of the day, after creating those bonds, it has an extra electron. This electron can actually flow in our material lattice easily, just like free carrier. So that's how it helps, by doping this kind of group 5 elements in the pure semiconductor, we can increase the number of carriers we have in that material, okay. So these are called donor atoms. So here we have used this antimony or SB. This is actually called donor atoms. And also these free electrons we are generating because of this procedure, these are called majority carriers. So we will see what's the difference between majority carrier and minority carrier later on. Similarly, we can say for p-type materials, whenever we have pure semiconductors and with that we have added group 3 elements like these, which will have 3 valence electrons. Okay, so here boron is one of the examples here, and you see it has formed bonds with other silicons, but one of the bonds is not properly created because it has lack of electrons, and this lack of electron is also can act as a carrier, flow of carrier. So these are called holes. So each dopant forms 3 covalent bonds, leaving one bond incomplete, creating a hole. Okay, so these are called acceptor atoms. So this boron we can call acceptor atoms. So what happens, this void of electrons or this lack of electron can also initiate carrier flow, because to fill this gap other electrons will come from other portion of this lattice to this portion here, and that will create another hole in another region. So in this way, so whenever we have holes, it can also initiate carrier flow, like that. So now this portion is important. So here we will understand the difference between majority carriers and minority carriers. So doping adds many electrons. So for n-type material, doping will add many electrons, okay, making the electrons the majority carriers. Here we have to understand, by doping in the pure semiconductor we induce or increase the number of carriers for n-type material, that is electrons. So this number of electron is quite high compared to the intrinsic carriers we have inside of our semiconductor. So you have to understand that. So thermal generation still creates electron hole pair. So intrinsic carriers, holes are present but in a very small numbers. These are called minority carriers. So you have to understand, whenever we have thermal generation in the intrinsic material, I mean without this doping, already in the semiconductor we can have some electron hole pair because of temperature, and from those electron holes, the electrons generated from thermal generation and also the electrons created by doping, these two added together are actually called majority carriers for n-type materials. Okay, the rest of the carriers which are holes are called minority carriers. So in this way you have to distinguish, for n-type material all the holes present which are only because of the thermal generations are minority carriers, and all the electrons generated, some from thermal generation, some from doping, all of them are together constituting the total number of majority carriers. Okay, so similarly we can say the same thing for p-type material. For p-type material we add extra holes by doping, and thermal generation will create electron hole pair, but the holes here generated and the holes by doping, these two will constitute total number of majority carriers for p-type material, and the rest of them, the electrons, will actually are the minority carriers. So here we can just see some visualization created for us to understand how they look like in n-type materials and p-type materials. So you see donor ions are here, majority carriers are here, minority carriers are here for n-type, right? So for minority so for n-type, holes are the minority carriers and majority carriers will be electrons, and donor ions are shown as positive. This is because whenever we have an atom and one electron is relieved from its atom outside, what will happen, in the nucleus the number of proton is higher compared to the number of electrons, so it is ionized, right? So it will be +1. So that's why these donor ions are showing as plus. So same goes for here, you see acceptor ions here, these are negatively ionized because one electron has come to it. As a result, the number of electron is higher than the proton numbers for atoms. That's why. Okay, now we will look at semiconductor diodes, and we will try to look at it in a very fundamental level and apply different biases, that means different voltages in this device, and observe how it behaves. So semiconductor diode basically means two materials, p-type materials and n-type materials are connected together creating a junction. This is called p-n junctions, and now for this case we have given 0 voltage applied. So we will see initially without giving any kind of biases how it behaves. So as you can understand, because p region have high amount of holes and n region have high amount of electrons, so there will be some variation of carrier concentration, and because of that some electrons will diffuse from n to p and some holes from p to n. So holes will go from here to here and electrons will go from here to here to make the number of carriers or charges equal in both of the regions, right? So this will happen and we call that diffusion, and this flow of carrier will obviously will initiate some current, right, which we are calling as diffusion current. You will see this diffusion current, this is actually happening because of this variation of concentration of carriers, and we are calling that diffusion current. Now as this is happening, obviously there will be some problem, which is, you know, as you can see, if holes are moving from this region to the n type region, some of the atoms will lose its hole, and same goes for n type, some of the atoms will lose its electron as it moves from n type to p type. And because of that, you see this region, some of the atoms are losing its electrons are becoming positively ionized, and here these are becoming negatively charged, and this particular portion here, this region is called depletion region with ionized atoms. And this because they are charged ions, they will create an electric field. And if you remember from your intermediate level, we learned that whenever we have a positive charge like that, and maybe with that very closely we have another negative charge here, if I want to know the direction of electric field happening because of these two charges, the direction should be from positive to negative, right? So same goes here. So the electric field generated here will have direction like this, E. We are calling that E, let's say. And this electric field, after being generated, it will try to oppose further diffusion. And also because of this electric field, a new kind of current is gonna flow, which we are going to call drift current. We will try to understand what is actually drift current, but for now just understand that whenever we have an equilibrium such that the diffusion current is equal to drift current, at that moment we will see that because of this equilibrium, now everything is stable. Now we will try to understand in detail what is diffusion current and drift current. So diffusion current obviously caused by concentration gradient of majority carriers. So basically in the p-type material we have excess amount of holes, and here we have in the n-type material excess amount of electrons, and as they are connected together, obviously they will try to create a balance of carriers charge, right? Because of that this current is flowing, and this is happening for only majority carriers, right? And for drift current, this is happening because of the electric field caused by diffusion current, right? So because of diffusion current, an electric field has been generated because of this depletion region, the direction of which is in this direction, so electric field. So it will actually help minority carriers to move. So if there is an electric field in this direction, that means what? So if we have holes here, so it can obviously move from here to here, and if we have electrons here, it can move from here to here because of the electric field. If you understand direction of electric field properly, you know that whenever we have an electric field in this direction, positive charges will follow its direction, right? So like this, and negative charges will actually go in other direction, like that. So that is what will happen, because in this region we have n-type material, and the minority carrier here is actually holes. So these holes will get swept through this depletion region because of this electric field, and also in this region the minority carriers we have is electrons. This will also be pushed by this electric field to this region. So drift current is happening only for minority carriers. Using minority carriers, drift current will flow, and diffusion current is only for majority carriers. And finally, what happens? First, we will have diffusion. Because of the diffusion, current will flow. This diffusion current will initiate electric field as depletion region, and that electric field will actually try to move the minority carriers from n type to p type and p type to n type. So that will initiate drift current, and both of this current, whenever equal to each other, will cause the equilibrium for our case, right? So at the end we will see no net current, because the amount of current because of diffusion will be exactly equal to the amount of current because of drift current, right? So we will see whenever we see equilibrium, we will see there will be no current flow observed inside of the material. That's why whenever we have not given any kind of bias, no voltage is given in this device, but still we see there are two types of current, diffusion current and drift current, happening at the same time. But because they are equal in value and also in opposite direction, they cancel out each other, and we don't observe any kind of physical current flow in the device before giving any kind of applied biases. So this is for applied bias, voltage is equal to 0. Now what will happen if we connect it in reverse bias condition? That means VD should be less than 0 volt. So the p-type material will be connected with the negative part of our voltage source, and n-type material will be connected with the positive side of our voltage source. What happens then? If you do that, electrons will be pulled towards the positive terminals, obviously, right? So here, whatever electrons we have in these n-type regions, the majority carriers, they will be attracted by this positive side, and also all the holes in majority, they will be attracted by this negative side. So as a result, what happens? More electrons and holes will move from their original position, this material p-type and this material n-type. So some of the atoms will lose its holes for p-type material, and some of the atoms will lose its electron for n-type material. As a result, the width of the depletion region, it will increase. Okay, so more electric field will be generated here, and as a result, what will happen? If this electric field generated because of this reverse bias, it is higher than before, so it will initiate that drift current we talked earlier. So this drift current, we will move the minority carriers, and we will see some current flow in the opposite direction, right? So oftentimes this drift current is actually called reverse saturation current or scale current. Reverse because it is in the opposite direction to the conventional current flow, and also saturation because the amount of minority carriers in this device is not changing, and it can change only if you can change the temperature. If you apply the voltage here or increase, decrease, and do anything, that will not change the temperature of the device. That means the number of minority carriers is still same. So even though you have increased the electric field here by increasing the width of the depletion region, but still you will see the saturation current, reverse saturation current or drift current, the amount is still same but in the opposite direction. So that's why the term is reverse saturation current or IS, you will see. But for majority carriers, we have got even wider depletion region with higher electric field, which is opposing the flow of conventional current, the diffusion current, right? So as a result, no holes will actually be recombined at the n type, and no electrons will be recombined at the p type. So there will be no diffusion current. So majority current flow is 0, but because of minority current, we will see that this reverse saturation current is happening. Now for forward bias condition, we will have VD is equal to a positive voltage. So here you can see this voltage supply, the positive side of that is connected with the p-type material and the negative side of that is connected with the n-type of our p-n junction. As a result, what will happen, it will push the electrons from n side and holes from p side towards the junction, because you see we have this positive side here that will repel any holes here, that will push the holes to go and cross the depletion region and recombine at the n type. And same goes for this n type region, the electrons will be repelled by this negative side of the voltage source, and as a result the electrons will cross the depletion region and try to recombine at the p type. So as you increase the voltage supplied Vd, obviously this push will increase, the amount of push will increase, and it will try to reduce the depletion region. So basically as you increase this Vd, you will see that majority carrier flow will increase because as the forward voltage will increase, the depletion region width will shrink even more. So there will be a certain moment when we have properly overcome the depletion region or the electric field that comes with it. We are trying to apply an electric field which in opposite direction to that, and when we properly fully overcome the electric field, we will see exponential rise in current in this direction, right? The diffusion current will increase in a very high level, and this threshold, whenever we have exponential rise in current, that this is called knee volt or cut-in voltage. We will try to look at that in a graph. So you see here we have seen for positive applied voltage or negative applied voltage how a diode behaves in terms of current, that is shown here. So this particular graph here, this is called IV characteristics. So very important for our electrical engineering domain. Whenever we try to understand about the characteristics of a device, always we try to look at the IV characteristics. That means for any voltage applied to that device, how the current is behaving, and with the change of voltage how the current can change, that is actually shown in this kind of graph called IV characteristics graph. So this is kind of the blueprint of every devices we can see in electrical engineering. So here I think you have already seen this graph, this is not new to anyone, but what we see is initially when you apply forward voltages to diode, initially no current is flowing because we haven't overcome the depletion region or the electric field that comes with that. Whenever we have finally overcome that, this is for silicon diode, so 0.5 volt. After that you will see gradually the amount of current is increasing, and the increase will gradually be more and more as we increase the voltage applied. So you see the current is exponentially rising here, and whenever we have 0.7 volt across our diode, we will see very high amount of current is flowing through our diode. So this is for forward characteristics, right? And this particular behavior is represented by Shockley's equation. So here we can see that ID is equal to IS e to the power Vd divided by NVt minus 1. So basically this 1 is coming from IS. So one portion is IS e to the power Vd divided by NVt, and another portion is IS. So this is the diffusion current happening in the forward direction, and this is the reverse saturation current or the drift current. And also this N value, this is taken as typically 1 to 2, but oftentimes it will be approximated as 1. So most of the times you will see that we are not using this N, and also we are omitting this IS because the amount of current IS is very low compared to this diffusion current. So as a result we can just omit that, and we will see that this is the approximated equation we will use throughout our calculation. So IS e to the power Vd divided by Vt, and Vt is the thermal voltage. You can see all of the details are given here. I don't think these are new to anyone, so we already know these things. Just some recap. Okay, now we will talk about diode models. So what are diode models? These are some approximation of diode behaviors we use in different cases based on our suitability. So there are models like ideal diode model, constant voltage drop model, then piecewise linear model, and also exponential model. So we will see each of them have specific purpose when we use them, and what is the benefit, what are the pros and cons for each of the models, each of the approximations we make. So initially we will look at the ideal diode model. So what is ideal diode model? So ideally, if we didn't have any kind of limitations for modeling our diodes, if we hadn't any physical parameters that gives behavior that is not desired, then this is the behavior we would have wanted. So for these kind of models, for forward biased, whenever we have applied a forward bias and it is in on state, we want the voltage drop across our diode to be as low as possible. So ideally this should be 0 and current should be flowing freely without any kind of resistance. So as you can see in this graph, whenever we have a positive voltage applied across our diode, the voltage across diode we are getting is 0 and the current is vertical line. That means it has no resistance. It is acting like a proper conductor with 0 resistance. And for reverse bias, it should behave like whatever voltage you give in the reverse bias situation, the diode should not conduct. That means ID should be 0 regardless of reverse voltage. So this is the ideal characteristics of diode, and we call this model as ideal diode model. This model is very easy to calculate, very helpful for understanding basic behavior of diode, but it will never give us the actual idea or actual value of voltage VD and actual value of current going through the diode IT for a particular case, but it will give some rough assumption which will make our calculations easier, but this model is not very accurate. Now for the next model, this is the exponential model and the most accurate model possible for modeling diode behavior. So what we do, we take the actual equations that govern our diode and the circuit. So here you can see this circuit, and two equations actually govern the behavior of this circuit. One of them is the KVL that can be applied in this circuit, and another one is the behavior of the diode itself. So by shortlist diode equation we can get the behavior of diode VD, so which is ID is equal to IS e to the power VD by VT. We earlier approximated that, so this should be the equation we should use to represent the behavior of diode. And we will see that another equation will come from this particular circuit itself. So here we can see the current going through the whole circuit is ID, which is equal to the supply voltage minus the diode voltage divided by the resistance. So it will give us the KVL of this circuit. So what is actually happening is we have two unknowns here which are ID and VD, and also we have two equations that govern this particular circuit. One of them is this KVL equation, another one is the diode equation coming from Shockley's equation. So if I draw both of these curves in a graph like that, in the horizontal axis we have voltage and in the vertical axis we have current, we are going to see these two graphs. So the straight line is coming from this KVL, very easy to actually put this value here. So what we do, to put this particular equation as a straight line in this graph, we will take in for one of the case ID is equal to 0. If ID is equal to 0 in this particular equation, then what should be the value of VD? That is the question, right? So so what we can do, I0 is equal to VDD minus VD divided by R, right? So we will see VD is equal to VDD from this case, right? So ID is equal to 0 and VD is equal to VDD. So we have got one point as x comma y, which is what? In the x-axis we have VD, which is VDD, and in the y-axis we have ID, which is 0, right? So this is one of the points we have got to, draw our straight line. So VDD comma 0 is here, VDD comma 0. So this is one of the lines here. And for another case, what we are going to do, we are going to put VD is equal to 0 in this equation and look at what is the value of ID, right? So then ID is equal to what? VDD divided by R, right? So in this case, the x comma y coordinate will be what? VD is equal to 0 and y value should be ID, which is VDD divided by R, right? So this point we can put here. So 0 comma VDD by R. So we have got two different points here, and if we connect these two lines, we are going to get the straight line representing this equation here. Very easy to understand. And now if you want to draw the curve that represents the diode, this will be like that, exponential curve, and the intersection point of these two curves will actually give us the value of exact VD and exact ID for this circuit. So at this moment, what is the voltage exactly we are getting for this circuit, and also what is the current going through the whole circuit, and also the diode. So this is a very good model for getting accurate results for diode voltage and diode current, but it is time consuming, as you can see. So when you are trying to do rapid calculations, we have multiple diodes and multiple different things. We just want to understand some approximated behavior of the circuit itself, then maybe this is not appropriate, because in this particular course our goal is to understand logic gates and how they are operated, how internally they are working. So in most of the cases, the logic levels we will work with is 5 volt and 0 volt, so kind of like binary, right? So that's why we do not need to be very accurate in terms of what is the exact value of diode voltage, what is the exact value of current, because in most of the cases we will have two different scenarios, one for 5 volt, one for 0 volt. So yeah, that's why this model is not appropriate for our course. And in this page you can also see that we have specific names for each of the cases, like exponential curve is the diode equation, and straight line is called the load line. Okay, so this straight line we have drawn here, this is called load line of this circuit, and when both of the curves are crossing each other, this point is called the Q point or operating point. This Q point is basically giving us the value of ID and VD. Now let us look at another diode model, which is the most important for our case, called constant voltage drop model. So what is constant voltage drop model? So in the previous case, in the ideal diode model, we saw that for forward biased case, we took the forward voltage drop of diode as 0 volt, which is not really that accurate, because for silicon diode also we have seen whenever the diode starts to conduct, at that moment the voltage drop across the diode lies between 0.6 volt to 0.8 volt, so it is not exactly 0. So that's why we have taken this approximation as 0.7 volt. So whenever this is forward biased and current is flowing, the voltage drop across the diode should be 0.7 volt, fixed voltage. So you see this kind of graph, right? So before 0.7 volt the current is 0, and after 0.7 volt we have a straight line in the vertical direction, because after that this diode will act like a pure conductor without any kind of resistance. That's why straight line, right? We can also model it as a circuit like that. So VD is basically representing the voltage drop across our diode, which is 0.7 volt for silicon, right? So in most of the cases we will see that this is the diode approximation model we will use for our analysis in our course, because this is easy to understand and easy to calculate. Also, this is not very computationally heavy, you will see. Okay, so the next one, piecewise linear model. So this is basically a bit better version from the constant voltage drop model, because you know, whenever we are talking about constant voltage drop model, we saw that after 0.7 volt we are assuming the diode will be short circuited, and you know, it will act like a ideal conductor with zero resistance. This is not the case. Obviously, whenever there is a you know, path for electron flow, there should be some resistance. So this is modeled by this, you know, slightly inclined line here. You can see previously for constant voltage drop model we saw that this was a vertical straight line, that means zero resistance, but here you will see there will be some resistance, and the slope of this resistance or this line will be 1 by RF. RF is the resistance of the conductor or the diode after it has reached forward biased condition fully, right? So this is modeled by this one. VD, which is the voltage across the diode, is 0.7 for silicon diode. After that, it will have ID multiplied by RF. So you see this portion here is actually represented by this one. So very easy to understand, and this is the equivalent circuit model of this model, piecewise linear model. Okay, so even though we have learned about 4 different models, for most of the cases we will try to use the constant voltage drop model, and sometimes maybe also the ideal diode model, but the other ones are not that important for our case, because they will make our calculation more difficult, and it will complicate things more. Okay. Okay, now we will move on to bipolar junction transistors. So already we know a lot about this device from our previous semester. In this lecture we will just briefly discuss about some of the things which are already known to you. So what is bipolar junction transistor? This is a current controlled semiconductor device. So here it's written, a small base current IB controls a much larger collector current IC. So we will try to understand that, but before that let us try to look at the device itself. So we have 3 materials stacked together. Here P, N and P, and here N type, P type and N type, they are stacked together, and because of that we have 3 terminals created. These are called emitter, base and collector, right? So what basically happens is whenever you have given some amount of voltage at the B or base, you will see some amount of current is going through the base. Because of that, in this path the current IC will also flow, and this is a current control device. That means if you increase the amount of base current here, so will this IC, right? So the relationship is kind of like this: IC is equal to beta IP, and the value of beta is very high, so that there is a kind of amplification happening. So comes in 2 types, obviously NPN and PNP, and we will see that there are 2 main applications for this device. One of them is amplification. Already you can understand from this one, it is kind of amplifies the amount of current, and also another one is switching. So mostly for our course here for this semester, we will try to use this device for switching, and how we do that we will try to understand in the next pages. Now one question to you is, why is it called bipolar, you know, bipolar junction transistor? Because current flow is happening because of 2 different kind of carriers or charges, which are holes and electrons. So holes and electron both are helping or constituting the amount of current flow in this device. That's why this is called bipolar. Now let us talk about different modes of operation of BJT. So here at the left you can see just a simple circuit of BJT. So terminals are given like collector, base and emitter. This is an NPN transistor, and the junctions, you know, these junctions are also named, like this is base to emitter junction or EB junction, and this is collector to base junction or CB junction. And based on how these junctions are biased, forward or reversed, we have different modes. Like cutoff mode is whenever we have both of the junctions as reverse bias, because you know, both of them are turned off and no current is flowing through here. So this is cutoff mode. and no IC current or IE current is actually flowing in this path. Then let us come to saturation. Whenever both of the junctions are forward biased, this base to emitter junction is forward biased and also this base to collector junction is forward biased, then we get this saturation and highest amount of current is flowing through this path, right? And then another mode is in between them, whenever we have a controlled amount of IBs flowing through that, and that is making this junction base to emitter is forward biased, but collector is at a higher potential compared to this base, then this is reverse biased, this junction is reverse biased. At that moment this device goes into a mode called active mode, and we get an amplification of current IB through this path. Okay, so this is what we are going to see. IC is equal to beta IB, because the value of beta is typically around 20 to 200. That means, you know, whatever current you push here as IB, that will get amplified here as beta IB or IC, right? So this particular mode is used for amplification. And then the fourth one, I don't think you have heard that before, which is called inverse active or reverse active. This happen whenever this junction, this base to emitter junction is reverse biased, but this junction base to collector junction is forward biased, then this inverse active mode happens. And where it is used, generally not that, you know, popular mode of operation this is, but we will see in our semester here for TTL logic families, we will see that this mode is used sometimes for some of the operations. So we will understand how this works and how it actually helps for this TTL logic family. Now here there are just some basic current and voltage relationships we need to know to understand BJT. Like you already know all these things. IE is equal to IB plus IC, so emitter current is equal to the summation of IB base current and collector current, and this relationship here. And for voltage relationship, you have to understand whenever we have active mode, the voltage from base to emitter VBE is considered approximately as 0.7 volt for silicon, and at that moment VCE, which is the voltage from collector to emitter, should be at a higher potential compared to voltage of base to emitter, because this collector should be at a higher potential compared to base, because they should be in reverse bias mode, this base to collector junction. That's why in active mode this is the requirement. And for saturation mode, we will see that, I mean, these are not that clear right now why we are taking these assumptions, but in the next page you will understand how these things are coming out. In the saturation mode also we have seen that both of the junctions should be forward biased, so that means this one should be forward biased and should have 0.7 volt, right? And also this CB junction should also be forward biased. Now if this is forward biased, that means this base should be at a higher potential of 0.7 to the collector, right? It's just like this one, but they are not doped in a similar way, this base emitter and collector junction. As a result, whenever this base to collector junction is forward biased, you are never going to see this kind of 0.7 volt voltage drop. Rather you are going to see 0.4 or 0.5 volt voltage drop. As a result, whenever you are taking the voltage from here to here, this collector to emitter, this should be what? This should be from this collector to emitter, which is minus 0.5 plus 0.7, so around 0.2. So that's why this is approximately taken as 0.2 volt for saturation mode. Okay, now we will look at voltage transfer characteristics of BJT. So what is voltage transfer characteristics? For a device, how the output changes for a change in input, this is shown in voltage transfer characteristics. So the parameters we will take is voltage, that's why voltage transfer characteristics. So input voltage, if it changes, how the output voltage changes for a device is gonna be called as VTC or voltage transfer characteristics. So for our case, this is the device. We are taking just one NPN transistor, very simple to understand, but here the input voltage is Vi and output voltage is V naught. So we will draw a graph where for each of the value of Vi, how V naught is changing will be shown. This is the voltage transfer curve. So let us look at the problem here. So they are telling us to develop the voltage transfer curves for the circuits shown in the figure below. This one, assume NPN transistor parameters of VB on is equal to 0.7 volt. So we are telling that whenever this base to emitter junction is forward biased, then the voltage drop should be around what, 0.7 volt. This is to be assumed, right? Then the beta value is given as 120, and also whenever we are in saturation, this is shown as VCE on, it should be 0.2 volt. This is what it's written. So whenever this is in fully saturation mode, then we are going to see that this is the collector, right? This is collector and this is emitter. The voltage difference between these two should be 0.2 volt. This is the thing that is written. So first, let us start from voltage Vi is less than 0.7 volt. If Vi is less than 0.7 volt, obviously this is not forward biased, so base cannot provide enough voltage for this junction to be forward biased. As a result, Q1, this transistor will be cut off, and as a result the current going through here IB should be equal to 0, and we know that IC is equal to beta IB. That means the current going through this path IC, it should be also 0. So that's why it's written IB is equal to IC is equal to 0. So then what should be the output voltage? So because the current going through this path IC is equal to 0, because there is no current going through here as IB is equal to 0, IC is also is equal to 0. So the voltage drop we are going to get here in this path, which is IC multiplied with RC, should be equal to 0. So whatever voltage you have given at the supply should be coming here in this collector junction, VC, let us call that VC. And VC is also V naught, the output voltage. So we can say that whenever we have Vi is equal to less than 0.7 volt, the output voltage V naught should be equal to 5 volt. Very easy to understand. Now let us look at another case where we have voltage Vi is equal to more than 0.7 volt. Then obviously if this voltage is more than 0.7 volt, it will help us to have a forward bias here. So VBE should have a forward biased condition, and this Q1 will get turned on, right? And for initial cases, obviously it will be in active mode because this is forward biased, and we have what, 0.7 volt, maybe more than 0.7 volt, but the voltage here, the collector voltage or supply voltage is higher than that. As a result, this junction here is revert biased and this is forward bias, so it is in active mode. So if this is in active mode, we can basically find the value of IB. IB is the current going through this path. IB should be equal to what, Vi minus the voltage we are going to get in this point, VB, right? So because this is forward biased, this is 0 volt, so that means this node should have 0.7 volt higher compared to this node. So VB should be equal to 0.7 volt, and this is what we are doing. If I want to find the value of current here, we should just take V1 minus VB divided by the resistance. So V1 minus 0.7 is VB divided by RB. So we have got the value of IB current. Now from that, let us try to also make our analysis go further. So then what we are going to do, if we know IB is the current going through this path, now we are going to get the value of current IC. We know that IC is equal to what, beta IB. Beta value is already given to us, right? So this is done here, and we have just replaced the IB value here. Beta is equal to 120, we know. And then finally we want to find the value of V naught. V naught should be equal to what, this voltage minus the voltage drop here, right? So V naught is equal to the supply voltage here minus this voltage drop, which is ICRC. and this IC can be found from this one, right? So this is just done here. So this is totally for just active mode. Whenever we have Vi is equal to 0.7 volt, we are taking this calculation and finding the value of V0, right? If you look at this particular equation, V0 is equal to this thing here. This is a straight line, okay? So straight line, and this is valid for whenever we have the value of V0 as 0.225. This is what you have to understand. If V0 is reaching 0.2 volt, that means what? V0 is actually VCE. You know that this node is collector node and this is the emitter node. So the voltage you are getting from here to here is VCE, C is V0, and E is equal to ground, connected with ground volt. So you can say V0 is equal to VCE, and we know for saturation case, whenever we have VC is equal to 0.2 volt, at that moment we reach the edge of saturation. We just start with the saturation mode. So that's why before 0.2, whatever voltage we have, if V0 is equal to 0.3, 0.4, 0.5, doesn't matter, still our device is in the active mode. Whenever it reaches 0.2 volt, at that moment it will go from active mode to saturation mode. So that is what is written here. So from 5 volt to 0.2 volt, V0 will behave like this thing we have done here as in active mode, and it will be kind of like a straight line, but we will see, we will look at the response how it looks in the graph. But let us now try to calculate for saturation mode as well. So whenever we have V0 is equal to 0.2 volt, so we have just reached the edge of saturation. So now based on that we can calculate again the value of everything, right? So previously whatever calculations we have taken here, this one V0 was equal to something, right? This thing was equal to V0. Now what we are going to do, we are going to deliberately write the value of V0, because we know for saturation it should be 0.2. If we do that and keep all the values as it is, we are going to get the value of Vi. If you calculate everything here, you are going to get Vi is equal to 1.9 volt. So what we can say is, Vi equals to 1.9 volt is the minimum voltage when we reach the saturation for this device. If we increase beyond that, we will still be in the saturation region, right? So that's why it's written Vi is greater than or equal to 1.9 volt, the transistor Q1 remains biased in the saturation region. So how it looks like, the whole thing, whatever we have done in the 3 different steps, we have found out the cutoff mode, we have found out the active mode, and finally we have got the saturation mode. Now let us look at in the graph. So initially when we solve for cutoff mode, we saw that for Vi is equal to 0.7 volt or less than 0.7 volt, we saw that output is 5 volt. So are we seeing that in the graph? Let us look at that. Whenever Vi is 0 to 0.7, this region, you see the output V0 is equal to 5. Yes. Then if you plot this graph here, which is a relationship between Vi and V0 for the duration of 0.2 to 5 volt for V0, you are going to see that this is the straight line you are getting. Okay, so for V0 5 to 0.2, this is the allowed region for active mode, and this is a straight line you see, but corresponding value of Vi should be 0.7 to 1.9, because we have seen active mode starts from 0.7 just after cutoff and up until the value of saturation, which is 1.9 volt, we see active mode. So in this portion you see, as you increase the value of Vi or change the value of Vi, proportionally the value of V0 will change based on the slope. So V0 will get amplified based on the slope of this active region, right? And then finally you see after 1.9 volt, if you increase the VIs, the output voltage V0 will be fixed at 0.2 volt. which is in saturation, right? You see. So now looking at this graph, you can understand how we can use this device in different applications. Like if we want to use this device for amplification, if we are giving some kind of voltage at the input Vi and getting amplification at the output, we are going to use this region, the active region, right? And if we want to use that as a switch, what we are going to do, we are going to use these two regions, the saturation region and this cutoff region. So basically whenever we have 0 to 0.7 volt as input, cutoff mode, and the output is fixed at 5 volt. And also for 1.9 to 5 volt as input, we are getting a fixed value of output 0.2, which is what we want. We want fixed value of output for this device to act as cutoff and saturation, right? In this way we can draw voltage transfer characteristics of different devices like BJT as well as MOSFET, and for different logic families you will see that this voltage transfer characteristics is different, and we can compare based on that which logic family is better compared to another one, looking by looking at this voltage transfer characteristics. Okay, now finally let us start with field effect transistors or FETs. Just like your BJT, FET is a 3-terminal device, but previously BJT was current control device. This is a voltage control device. So you can see there is a comparison between them. So whenever we have BJT, we given a current IB, and based on that we got amplification in IC, right? Here we have to give some kind of voltage here. So you have to understand that just like BJT, this was base, this was collector, this was what, emitter. The 3 terminals of FET is called what, drain, D, this is gate, and this is the source, and we have to apply some kind of voltage here from gate to source called VGS, and based on this voltage the current will flow in this path, right? So this is the main difference between these two. So let us look at some of the key differences. Let us try to explain them. What is the difference between FET and BJT? So the first difference is in terms of control type. So BJT is current control and FET is voltage controlled. Conduction, BJT is bipolar. So we already looked at that. Like for BJT, the charge carriers are of two types, electrons and holes, but as you will see or as you have already seen in the previous semester, FET only have one type of carriers for one type of device. If this is N channel, that means electrons will only flow in the channel, and if this is P channel, that means only holes will flow in that channel. So in this way, and because this is voltage control device, and we will also see there is a insulating layer for FETs of silicon dioxide or something, the input impedance is very high for FET compared to BJT, because current cannot directly flow through the device from the gate. So from the base to emitter, some current is actually flowing from here to here, but for FET from gate to source no current is actually flowing, you are applying some voltage, and because there will be one insulation layer here of silicon dioxide, charge or carriers cannot directly flow from gate to the actual device. So we will in detail we will see that. And then voltage gain, generally BJTs have higher voltage gain compared to FET, and temperature stability, FETs are more stable because because this is voltage control device, and the current consumption is less compared to BJT. That's why power consumption will be less, as well as it will be more stable compared to BJT. So these are some of the benefits we are getting for field effect transistors compared to BJT. So that's why these are prominently used nowadays. Previously BJTs were more renounced and more popular, but nowadays because by using FET we can design our devices in a more compact manner. That's why FETs are more suited compared to BJT nowadays. Now there are two main types of FETs, JFETs and MOSFETs. So MOSFET is the one we will specifically focus on for this semester, because this is widely used in digital logic gates, not JFET. So that's why we will talk about these things. We will in detail look at the architecture of different MOSFETs. Okay, so MOSFET means metal oxide semiconductor field effect transistor. So why metal oxide? Because when we will look at the gate structure of any MOSFET, it will have a metal layer which is separated from the semiconductor by using an insulating oxide layer like silicon dioxide. Okay, so that's why this metal oxide is written here. And field effect, why field effect? Field effect means like how the device controls current using an electric field created by the gate voltage. So again, if we look at the picture with some example, it will become more clear to you. But compared to BJTs, the approach we take for MOSFET is quite different. So what we do, because there is an insulating layer from the gate to the actual device itself, we are giving different kind of voltages at the gate to source. So because of that, some electric field is created but no physical connection. So this is kind of inducing, but not physically the charges are flowing from the gate to the device itself. As a result, we are calling that this is a field effect. Electric field is causing this change, not actual charge flow or carrier flow. Okay, so now we know that different kind of MOSFETs are there, depletion type MOSFET and enhancement type MOSFETs. But up to this day, the only type of MOSFETs we see prevalent in digital logic design and also in different ICs in our processors is this enhancement type MOSFET. This is the actual type of MOSFET we use always. So that's why our discussion will be only constrained into this type of MOSFET, and let us try to discuss the architectural detail, inside detail, how it works. So in the left figure, we are just taking one example of n-channel enhancement type MOSFET. So now we can in detail discuss what we have talked about. So the insulating layer we talked about here, this is the silicon dioxide layer here, which is separating this gate terminal to this whole device itself. And as you can see, this is the drain, this is the source, this is the gate. So drain is connected with a conductor with some n-type material here, and source is also connected with some n-type material, n-doped region here. And the whole thing, this substrate is actually p-type material. Now what we need to do here is somehow try to create some kind of channel here so that electrons can flow from drain to source. That is our goal. But as you can see right now, the p-type substrates will have abundance of holes, not electrons. As a result, we cannot have enough amount of electrons here that will help transport of current. So that is not possible. So this is the general architecture. So sometimes you are going to see that this substrate is directly connected with the source itself, and sometimes it is kept open so that we can deliberately connect it with anything we want. So let us look at how it actually works. So key construction features, I think I have already discussed most of the things it is written here. So we have talked about substrate. So substrate is basically this p-type material here, often called as SS. So generally it will be connected with the source for both of them to be in the same potential. And in contrast to depletion type MOSFET, this enhancement type MOSFET has one difference. If you look at depletion type MOSFETs, you will see that a channel is already built here, which helps this electron transport or hole transport whenever needed. But here we don't have this kind of thing. So somehow we have to apply some voltage somewhere so that we can create this channel for current flow. And another thing is this silicon dioxide insulating layer. Because of this insulating layer, whenever you are applying any voltage here, no current should actually flow from gate to this device itself. No charge carriers, anything should not flow from here to here. What is happening? By applying voltage, you are applying some kind of electric field. Because of that, electrons and holes will be affected because of the electric field we are giving, but physically no electrons or holes will flow from this flow across this silicon dioxide layer. So that's why we are saying that field effect term is being used in MOSFET, and also this is the reason why MOSFETs have a very high input impedance. Now let us look at different behaviors for different applied voltages. First of all, you have to understand that the applied voltage, the voltage we are going to apply is in terms of gate to source. So we are going to connect one voltage from gate to source gradually, but initially we are keeping these two as open, so no voltage is being applied. If you do that and apply some voltage at the drain compared to S, so we are going to apply some voltage from drain to source like that, but no voltage is coming from gate to source, so we can just short circuit those so that they are in the same potential. So if this is the case, no channel is created here and no current ID, drain current, will flow from here to here, right? So even though we can see some electrons are here, some electrons are here as majority here, but the path has to complete. If there is no complete path, no current should flow from the drain to source. That is what will happen for VGS is equal to 0 volt. Now let us look at behavior at VGS is greater than 0 volt. So whenever we have VGS is greater than 0, so some positive voltage will be applied to gate compared to source, and also you see drain to source voltage is still positive, so VDS is positive and VGS is positive. What will happen then? So as this voltage is positive and substrate is connected with the source itself directly, that means there will be some potential difference between this gate to substrate as well. So as a result, this is positive voltage, it will try to repel all the holes from here in the substrate region and try to attract the electrons towards it. As a result, what will happen? This kind of channels of electrons will be created as you increase the VGS, okay, and this channel will be much more prominent. So there is a term called threshold voltage, which is the minimum gate to source voltage to be applied for this channel to be formed. Okay, so when we have enough amount of voltage applied higher than threshold, we will say significant amount of electrons are stacked here and all the holes are repelled to the deeper regions of the substrate. As a result, this channel will form, and because the drain is at a higher potential compared to the source, the current will start to flow from drain to source. Okay, now why this particular type of device is called enhancement type? Because by applying this VGS, you are enhancing or creating this channel for current flow. That's why enhancement type. And current ID will increase, the drain current will increase as the VGS gets increased to a higher level beyond the value of VT. So that will happen. And there's another term called pinch off, which is quite important. So let's say if VGS is fixed, but if keeping that VGS fixed, we keep increasing the value of VDS, so drain voltage compared to source voltage keeps getting increased, what will happen? VGD, the voltage from gate to drain, okay, so this will get decreased. Why is that? Because gate will have the same voltage, but as you are increasing VDS, so drain voltage will increase, so VGD will decrease. And if you remember, we have this N region here, N type region here connected with this P type substrate, and if drain is at a higher potential compared to this substrate, or as well as this gate. This is also kind of affecting this substrate because it is using electric field to control the holes and electrons here. So what that means is this p-type substrate will be at a lower potential compared to this drain. As a result, this is reverse bias. This region here is actually reverse bias, and there will be a depletion region created because of this situation. As you increase the value of VDS, this width of this depletion region will increase, and as a result you will see this kind of narrowing of the channel because of the depletion region. And at certain point we are going to see that pinch off is happening. So even after increasing the value of VDS, we are not going to see any kind of increase in current. It will get to a fixed value, or a saturation will happen. This is called pinch off. Now if we understand all this, we just have to understand this thing that for this device, what we are doing, we are applying some voltage at the gate compared to the source. So VGS is applied, and at that moment, if the drain is at higher potential compared to the source, current will flow from drain to source because a channel is created, right? So this is the basic function or basic architecture of enhancement type MOSFET. So now let us look at some of the circuit symbols we are going to use throughout the semester to represent P channel as well as N channel MOSFETs. So these are the three possible circuit symbols you can use for N channel enhancement type MOSFET. This is the most conventional one initially used in the books. So this is actually the substrate, you can see, and gate, source. So if you apply a VGS positive voltage, current will flow from drain to source as ID whenever we have a positive VDS applied. And sometimes you will see that this is directly connected here like that. So that means the substrate is connected with the source directly. So the next symbol, this is the more simplified version, you can see. And in our semester we will try to use this circuit symbol in most of the cases. And this is the third one. This is mostly used in digital logic design. Sometimes whenever you have a very big design, this is the most simplified version. But sometimes there is a problem, which is the drain, which is the source. It is quite difficult to understand for this symbol because we don't have any kind of arrow symbol here. So that's why we will try to avoid this one and try to use this one in most of the cases. And same goes for this one, P channel enhancement type MOSFET. So here we can see three possible circuit symbols here. This is the most conventional one, but this is the simplified one, and this is the one we will try to use. But one thing you have to understand, the difference between P channel and N channel is generally for N channel you give positive VGS and current flows from drain to source as you give positive VDS. Here as you can see, source is at a higher potential compared to drain. So we have given what? VSD as voltage, and also the gate voltage we will apply will be negative. So VSG is given, so gate will be at a lower voltage compared to the source. If that happens, then we are going to see this current going from source to drain, which is ID, right? So so these are the two circuit symbols we are going to use for P channel and N channel. In most of the cases we will try to use these things. Then finally we have come to the end of this lecture. So we have briefly discussed about some of the basic electronic devices we need to use for our semester here for building different logic gates, diodes, bipolar junction transistor, and MOSFETs. So finally, in this last page, let us discuss about how MOSFETs are used in logic gate application. So here you can see this is just a structural diagram of an actual enhancement type MOSFET. So everything is shown here in a 3D diagram, and you can see that we have defined a length here called L here, which is the distance from drain to source, right? And this is the width, and this is the polysilicon or metal used for the gate, and this is the insulator or silicon dioxide material to isolate this material from the conductor here. So yeah, now finally we will see in our course here. In most of the cases we are never going to say n channel enhancement type MOSFET. These are named as NMOS, and p channel enhancement type MOSFET will be called PMOS, and these are directly sometimes used for creating different logic gates, as you will see. But both of them have some drawbacks in to be used individually. So that's why later on there was a new architecture called complementary MOS or CMOS was designed, which combines NMOS and PMOS. So we will learn the architecture of CMOS, how it works, what are the electrical characteristics, in everything will be known to you. But generally what we have seen is, compared to other logic families or other technologies for building logic gates, this particular technology of CMOS offers lower power, high noise margin, and high density. So we will learn what is actually noise margin in the next lecture. But generally this is better in most of the cases compared to other technologies. That's why still to this day CMOS is used to build different logic gates and processors and every kind of digital electronics devices. So our focus in this semester at the beginning will be to discuss about these different technologies we use to build digital electronics devices. So it can be whether with diodes or MOSFET or bipolar junction transistors. So different things will be used to build different architectures, and we will look at the electrical characteristics, how they are good or bad in different characteristics compared to each other. So these things will be discussed in this semester. So that's all for this lecture. Thank you.